Okay, everyone, I'm Heiko. I'm also one of the Shogun contributors, and I'm currently doing a PhD in London at UCL. And I'm going to talk about a few random things that you can do with kernels. In particular, I'll be talking about Gaussian processes, which are like a building block of many state-of-the-art machine learning tools for regression and classification. So I'll talk a little bit about the basic fundamentals of Gaussian processes, so just the basic ideas, how do they work, and some applications. In particular, how can you cast regression or logistic regression problems as Bayesian inference. And on top of this, I'll go a little bit into model selection, which turns out to be possible in a quite nice way. For example, nicer in the SVM framework. So the reason I talk about this is because last year in Google Summer of Code, we had a student, Jacob Walker. He implemented a regression framework in Shogun with these Gaussian processes. And this year, I actually mentor a guy called Roman from Siberia, apparently, who's implementing some classification models using Gaussian processes. And then the talk is like split into two halves, or in 2/3, 1/3. And the last third is I'll talk a little bit about what you can do, how you can embed probability distributions into kernel spaces. And this is something that is more cutting edge. There's a lot of research done at this at the moment. I just introduced the very basic idea and introduce you to some tools that you can derive from this to sample testing and independence testing. And we also have this in Shogun. Actually, I implemented this last year in the Google Summer of Code. So if you ask yourself, is there any relation between those two subjects? No, there isn't. But based on these votes we had on the website, we just wanted to talk about both. Yeah. So Gaussian processes. These are, as I said, these are a quite useful tool. And by now, you should have got an idea about the usual classification and regression problems. So when you get like clouds of points in some space, you might want to distinguish between two colors, like here, and you might want to get like a distribution of labels over the full space. So you might just be interested in something more than just these decision boundaries here, where the classes are discriminated, but also in like how probable are the classes. And for regression, I plotted a quite neat example here from a book, which is a measurement of CO2 over the years. So on the x-axis there's year, and on the y-axis there's CO2. And you kind of see two types of structure in here. First of all, you see this linear trend that CO2 levels are increasing, but you also see this annual up and down thing, which you might think of might be caused by heating in the winter. And you can model these things quite nice with Gaussian processes. And here is shown the output of a Gaussian process regression model, and you kind of see some kind of uncertainty going on. So the more you move away from the data, the less confident the model gets in its predictions. So let me tell you a bit about Gaussian processes, and especially why I like them a lot. So first of all, they're Bayesian. If you don't know what that means, don't worry too much. You'll understand it after the talk. So first thing it means is we have a full probabilistic framework for what we're doing. So with SVMs, you have all this geometry going on with margins and hyperplanes that are separating the data. And then you predict on which side of a hyperplane something is to predict a label. For Gaussian processes, we actually also get something. We get a calibrated confidence level, which can be interpreted as a probability. And we don't have to do any hacks to do this. So with SVMs, you can fit the distance from the hyperplane through some sigmoid function and then get a scaled probability. With Gaussian processes, you get these directly. And second thing is, these models are actually aware of uncertainty, and they're able to quantify uncertainty. So an example for this is, why is this even useful? Imagine you have a linear model, and you just try to fit it to some data. So you have some blue points, and you fit a linear line to it. And then you you pass the distance from this line through some sigmoid to get a probability, and what you get is something like this. So you get high probability on the line, and then further you move away from this, the less it gets. So actually, at the borders of the image, there's not a lot of data, but your model still tells you, I'm quite sure where the data is, where for any x point the y point is. This is not good, right? Because you don't have any evidence for this. So when you do this as a Bayesian inference problem, Bayesian regression, what you get is that your model only is confident in areas where you have a lot of data. So here it will still output the same prediction, but you get a certainty level which is much lower, so which tells you I'm actually not quite sure what's going on. And you can use these two properties to do model selection within the framework without doing some type of grid search or trying out all the combinations. So here we have some data again, and in both sides the points that you were seeing are actually equal. And here are two models. So I have this suggestion and this one. Which one do we take? This is might be hard to answer, but actually in this framework we can answer those questions. We could select the best one, we can quantify this, or we could actually just use both, or even more. But I'll come back to this. So then, next thing is Gaussian processes are a non-parametric model, which means that we don't pose any assumptions to how the data is generated. So not like linear regression, we say data is linear. We don't do this. And in fact, there are many connections to this plain kernel method idea of embedding points into a high-dimensional space, do some kind of linear model in there, and then map it back. So there are many relations. And the way this is done with Gaussian processes is that you define distributions over model functions, and those functions can have basically arbitrary forms, and you can manipulate them, and this way you can do predictions. So here's a picture I'll use throughout the talk that I stole from a book. So you kind of define a distribution over functions that are within a certain band that is plotted gray here. So these functions here are one-dimensional. You have many of them. And then what you do is when you have some data, training data, you kind of pick the functions of all those you have that explain your data to do predictions. And last thing is Gaussian processes are actually quite simple. So you just need 3 mathematical ideas to understand them. Sometimes, as with everything, there's a lot of technical stuff going on. But I won't talk about this too much. I'll just talk about the ideas. And the ideas you need is, first of all, the sum rule. So some rule to integrate out a variable over a joint distribution. So if you have a joint distribution over 2 random variables, you can just sum over one of them to get the marginal distribution of one variable. And this is the discrete case with sums. This also works for integrals when you have continuous distributions. And second rule is Bayes' rule. Should be known to almost everyone who ever did a statistics course. This just tells you if you have some prior belief about something, then how does an observation change this prior belief? And you can formalize this with saying, well, I got some prior distribution over a variable, and then I got some observations. How do those observations change my prior distribution into a posterior distribution? And then for this marginal term down here, actually you can always apply this sum rule here to get this form of Bayes' rule. It's like the one that's usually used. Okay, and the last thing you need to be able to do is you need to be able to manipulate Gaussians, which is also not too hard. So if you have some kind of joint Gaussian distribution, which I'll write as this calligraphic N, here are the means, and here's a covariance matrix. So if you have a joint distribution over 2 Gaussians with this covariance, then all these objects here, like if you condition on one variable, if you integrate out one variable with the sum rule, or if you just multiply 2 Gaussians, all of the distributions you get are actually also Gaussian. And this is a very important property that we'll use when constructing the Gaussian processes. So I've not written the details here of those things, But the key point is, if you do something with Gaussians, you basically stay Gaussian. Okay. Now, what is a Gaussian process? This is the plain definition. Gaussian process is a collection, might be infinite, of random variables, of which any finite subset has a joint Gaussian distribution. We usually write this as in this form. So we say we have a Gaussian process and we have a mean function. So if you take all the functions of the Gaussian process and average them, you get the mean function. And then we have something which is called a covariance function, or kernel. It's actually the same thing as a kernel. This gives you the covariance between functions of the Gaussian process evaluated at 2 different points. But I'll talk a little bit more about this later. This is the plain definition. So now we might wonder, how do these functions look like that I'm talking about? Yeah, we can actually sample them. We can just plot them. So I'll introduce some notation for data. So I'll say X is our training data. It's just a collection of numbers, of vectors, covariates in general, and some testing data, X star. And then what I'll do is, we want to plot functions of the Gaussian processes evaluated at those points here. And I'll collect all the function values on all these points in these bold Fs here. And then last thing is, I'll use kernel matrices or covariance matrices, and I'll use this notation for this. So this is the matrix you get when you plug in all the values of X and X star into the kernel. So if our functions F are from a Gaussian process, they are jointly Gaussian distributed. So they take this form here, just a joint Gaussian distribution. And this has a very simple form here. So you just have the kernel matrix of the training data with itself, you have the kernel matrix of the test data with itself, and then you have some cross covariances in between. And I've chosen a 0 mean here to make things easy. So those 2 things are jointly Gaussian distributed. Now we can, since this is an easy distribution here, we can just sample from it. We can just take a random element from it and plot it. And this is what we'll do. And what we'll also do is, we can ask ourselves, how does the function of the test data behave if I've seen the function of the training data? And this basically means that we condition on one of the random variables. And as I've told you before, if you have a joint Gaussian distribution, conditioning on one of them is still a Gaussian, and it has some ugly form. You don't need to care about this too much, but it's fairly standard. And then you have your distribution over the Fs. So now here are those 2 plots again. So here are samples from the functions of a Gaussian process where I've just seen the training data. So what I do is, I take all my training data, I sample from this Gaussian here, and I just take the upper part, and I just plot them as a function. So then I get these, because I have only finitely many points, like these are the training data. And if I connect them, I get these lines. So I get all these different functions here. And kind of all of them are equally probable. And if I do this conditioning operation here, this F star given F, this means how does the Gaussian process change if I've fed it some training data? Then I get this. And this is a very nice intuition. Kind of means that, so I have all these functions. And now I just only want to take those functions that go through my training points. And this way I have a distribution over functions. This one is again a distribution that all might explain my training data. And this is the basic idea. You can later on then use all those functions to do predictions in the areas where you didn't have training data, right? But there's sometimes our observations, we don't want these functions to go through the observations directly, because we might assume, well, our observation process it's not really accurate. There might be it might be inaccurate, so there might be some noise in the observations. So what we do is we introduce a likelihood. So given such a function here, we define a probability of how likely some data is given this function. And then what we do is we model the data with a joint distribution over the labels of the data. These might be the y values for some x values, or these might be labels, plus minus 1, for some images. And we write this joint distribution, again with one of those simple rules, as a product of the prior of the Gaussian process and with the likelihood of the data given a latent function. For example, if we want to do regression, and as I said, we kind of assume that there's some noise in our observations, we just use a normal distribution with mean of the latent function. This basically means the observations, the probability of the observations are given by a latent function to which we added some noise, and then we just compute the probability of this. Another example, if we, for example, want to do binary classification, we just choose an activation function, which might be looking like a sigmoid, so a function that goes from 0 to 1 at some point, like a continuous step function. And then we just take the product of those for all the data. Then we get a likelihood which we can use for binary classification. I'll show you an example in a minute, but there are many more likelihoods that you can use. For example, there's a multi-class logit function which you can use to do like a native multi-class classifier with no need for any competitions like one against one or one against others, while still obtaining calibrated probabilities and staying within your Bayesian framework, which is nice. So here's an example for a likelihood which can be used for binary classification. It's this logit function here, it's a sigmoid. It's just this standard form here. So what I've plotted here is a very simple data set. It's one-dimensional on the real line, and you get labels red and blue. And now here I've plotted a latent function that happens to explain those data quite well. So it's large for any area of the line where you have many red points and small where you have blue points. And then what happens when you use this likelihood here, you kind of squash this latent function to get something between 0 and 1. So the function you get is this. And it kind of has the same shape, but this one is between 0 and 1, so you can interpret it as a probability. So in this way, you can model your classification data, right? And there also, you can imagine there are other ways of doing this, getting from a latent function to a probability that kind of explains your or resembles your data. Okay, now here comes this is the most challenging idea of the Gaussian processes, in my eyes at least. Now we want to do predictions. Now we had all these functions, and now of those functions we took only functions that can explain our training data. Now, how do we do predictions with this? Because since we have a distribution over functions, we still have infinitely many that might explain the training data. So in here I just plotted 3 of them, but all those functions in this gray area are very probable to have explained the training data. How can we use those for predictions? Well, the answer is we just use all of them and average over them. This is like the principal idea of Bayesian inference, averaging out over many models. So recall we had this joint distribution of data and this latent. Now what we want to do, let's formalize it. Given some data y, so our labels, for example, red and blue, and our covariates, which were before just points on the real line, but might be plastic apples versus natural apples or similar. So we're interested in label predictions for unseen covariates, so things that have not yet been revealed to the Gaussian process. And we can write this down as a distribution of our labels given the labels that we have observed so far. Well, since we have a joint distribution over our f's and our y's, we can use the sum rule from the beginning. Easy rule. So we can think of this as if we had a joint distribution over the f's for those y's here, f star for y star, and we just integrated them out. And then we again rewrite this in this conditioned form here. So likelihood times distribution of f. And then what this integral here means, it just tells us, well, take all possibilities of those f star and average the likelihood for our unseen data over them. This way, we actually get a prediction over a prediction for our new label, right? But the nice thing is here we get a full distribution, and then we can take, for example, the mode of the distribution, the maximum probable thing, or we can do something else with it. Okay. This is the general way to do this Bayesian inference, but now in Gaussian processes the problem is, well, what is this here? I haven't told you what this guy here is. The distribution of the Gaussian process functions given the observations of the training data. Right, so we need to know this. And here again, as we've seen before, the distribution of the latent variables over the training data and on the test data, they are jointly Gaussian. This is just the definition of a Gaussian process. So we can again write this down with our sum rule, right? So we can write this as the distribution of the f star given f, which is the latent functions for our training data, times this distribution here. So how do the functions look like given that I've seen some training data? Okay, and now here the troubles start if you want to do this. We know this one here, right? I've shown you plots of this before. Those are the functions that go through the training data. But what's this here? We also need to do this. So we apply Bayes rule. This was the second rule that I told you before. And we write this here, we interpret this as a posterior distribution of the y over the f, given those y points here. And we just apply Bayes rule. So we just flip those arguments, multiply it with the first variable, and divide by the second variable, again with sum rule here. So we have this one here. And now in order to do our predictions, we need to compute this, right? If we have this guy here, we can plug it in here, then we can compute this integral and have this distribution. And then we can plug this in here and do our predictions. So it's 2 steps. Okay, now for the regression case, I've told you that the likelihood is Gaussian. It's just some noise added to the latent function. And this is really nice, because if I plug a Gaussian up in here, then I have this guy here, it's Gaussian, observation likelihood. This one here were the functions within the band. It's also Gaussian. This is from the Gaussian process. So I have 2 Gaussians, I multiply them, I stay Gaussian. Same happens for this guy here. So this guy is Gaussian, plug it in. Gaussian, Gaussian, integral is easy. Plug it in here. Gaussian, Gaussian, integral, Gaussian, everything's fine. We can analytically write down the distribution. Now here's I hide some technical stuff from you, right? So I always say we integrate over Gaussian, but this is really easy. It involves a lot of symbols if you write it down. But actually it's just the line under a Gaussian bell curve that we do here, just over and over again. So it's very simple and it's easy to compute. So for regression, everything's fine. Now if we do binary classification, things get a little bit more messy, because our likelihood is a sigmoid function, which is not Gaussian. So this one is not Gaussian, and we are kind of sad about it. But then what we do instead, we just approximate with a Gaussian, and then do the old thing again. Yeah, again, I'll skip the details, but basically what you do, you match the first 2 moments of the distributions. So you find the maximum, for example, via Newton optimization, then you do a Taylor expansion around the mode, and you just plug it in and you get everything. Might sound a bit complicated, but actually in practice, this is very easy to solve. It actually, when you code this up, it's way easier than writing an optimization algorithm for SVMs. So, yeah. There are many more methods to do inference here. For example, variational methods that optimize lower bounds on errors, or even sparsity methods that kind of throw away most of the training data and only keep the points that are interesting. But yeah, this would be too much. So now we can do inference, right? So now we can solve, we have training data, we have test data, we have a fixed kernel. I can tell you the distribution of the labels of the test data now. But what I haven't told you is, well, the kernel might have some form and some free parameters also. And actually also the likelihoods might have free parameters. So imagine we had this what was it? Sorry, we had this regression likelihood. It has some noise parameter. How much noise do we assume in our observations? Or imagine you're a biologist and you're doing some kind of Poisson models where you count things. Then you have a decay rate. You also have to specify this. So I have the example here of the Gaussian kernel because we're mostly machine learners. So I've written it as this form here, some exponential of a negative L2 thing of 2 different points. I've added a scaling parameter here. This is usually done in statistics, not in machine learning, because in machine learning it doesn't matter. But anyway, this parameter here controls the width of the bell shape. And for the Gaussian processes, this has a really nice interpretation in terms of model complexity. So I told you the kernel that you use gives you the covariance between functions of the Gaussian processes evaluated at 2 different points. So imagine the covariance of points is small. So if the kernel is very small, the covariance of 2 function at distant spaces will be small. And this means the functions can basically fluctuate around wildly. And with functions that fluctuate around wildly, you can basically explain anything. Whereas if the kernel is very large, the covariance between 2 functions evaluated at distant points will be large, which means that the function cannot do what it wants. It has to stay smooth. Which parameter do we take now? And now here's again this little nice picture. 2 pictures of the same data, 2 models. Now which one do we take? Both of them actually look reasonable, right? So we go to the machine learning guy and we ask him, hey, machine learning guy, what should we do with our parameters? And he tells us, just select the best parameter. We think, is that really reasonable? Because actually both of them look reasonable. But let's do it anyway. How do we do it? And he just tells you, well, just do a grid search. Just try out all the combinations. And we think, oh no, this is not nice. Let's do something which is more nice. And now recall this. This is the numerator of the base rule. This is the thing below. And this is just the probability of the y's. Now I've added some theta here. I'll tell you what this is later. And again, using the sum rule here, once again, we can write it as some likelihood times some Gaussian process prior. And now I've made this thing dependent on the hyperparameters theta, which could be, for example, the kernel width and the kernel scaling. So this is now the likelihood of the model averaged over all the models that are that we consider, right? So those are all the functions of the Gaussian process, and this one gives the likelihood. This function is actually, it's available when we can do inference. We can also compute this here. So we can also maximize this. We can compute gradients, and we can do some kind of optimization on this. So when I tell you, well, we maximize likelihoods, should always say, oh, well, what about overfitting? If we just maximize likelihoods, we might just choose the model parameters that just explain the model, the training data really well, fluctuate around wildly, but don't explain any test data. But actually, no, this doesn't happen within this framework, because we're averaging over all the F. Let me show you a picture for this. So now imagine we chose an immensely complex model, so the function is not really smooth, it's doing wild things. These functions come from a distribution, and probability distributions have to integrate to 1. So the thing is, if our model class contains many Fs that can do different things, each one of them can only get a low probability. Whereas if we have a model class which contains only few functions, we can get higher probability values for each of them. And so this thing is known to the machine learning community as Occam's razor. And it basically tells you how complex, it answers the question, how complex should your model be if your model data. So as I've told you, imagine your F here is doing weird things. If we look at this graph, where on the x-axis I've plotted like all possible data sets there, and on the y-axis I plot the marginal likelihood, the probability of the data given the model. If we choose a model that is very complex, we can explain a wide range of data sets. But since we have to integrate to 1, each of them gets a low probability. Whereas again, if our model is too simple, we can get a high probability, but only for a small amount of data sets. So which model should we choose? Obviously the one that is able to explain our data set, here D0, but just this, not more, right? And if you again look at this integral, exactly this happens here when you maximize this. You exactly go for this red line here. And this is a nice thing about Bayesian inference in general, that you have those kind of effects. You can just maximize a single likelihood function, but if you average over all the models, this is fine. Now we can choose the best parameter. But now we plot the surface of this likelihood function, and we observe, oh shit, there are two maxima, and they have both the same amplitude, which actually corresponds to those two here. So we ask the Bayesian guy, and he tells us, don't just use the best one, just use all of them. And this is what we can do. So this is something more sophisticated, but in theory, the Bayesian framework allows these Gaussian processes to compute posterior distributions over the parameters. You can learn them from the data, and then you can average over all these parameters that might explain your data well, and then you can average your predictions. And especially for very small data sets, you can imagine that this might happen, that there might be a lot of models that can explain your data. So you want to take into account all of them. And especially if you're doing this, your uncertainty estimates that you get along with your predictions are very accurate. And usually, in those cases where you have a lot of classes, you don't have so much data, usually these Gaussian process type of models, which integrate out the model parameters, they perform really well. So for example, they do usually much better than some kind of one-against-one sport vector machine where you then fit sigmoid functions and use all sorts of heuristics. But this is really tricky. So in Shogun, we can do this. We can do this maximization, but we can't do this yet. But we're working on this. I'll show you a demo of this actually now. I don't have a Mac at home, so sorry. Here you go. Okay, here's a little demo for. This is good. So this is a little demo Gaussian process regression. Oh, there's Probit. I want to have the other one. Yeah. So this is a very simple regression demo, how you would do it in Shogun. So first of all, you import some stuff. Zoran has showed you this. Then I generate some data. And here I just choose a sine wave. I evaluate it at random points and add noise. So pretty simple data. Then I pass everything to Shogun, make sure that the dimensions fit and everything. And then here, this is how you set up this Gaussian process framework. And the way this is done in Shogun is quite neat. It's very modular. You have different likelihoods, you have different ways of doing inference, and you can just plug them together. So here you generate your kernel, you pass it here I choose some predefined kernel size. I create a mean function for the Gaussian process. I didn't talk about this really, but just choose 0, that's a popular choice. I create a likelihood function, which this one is the Gaussian likelihood, so just plain regression. It has some observation noise parameter. Then I create an inference method, which is the way of solving all those ugly integrals we've seen before, which for the Gaussian likelihood we can do analytically, and this is done in this class. And then I just pass the inference thing to the Gaussian process. And the Gaussian process is, again, it's implemented under the machine framework in Shogun, so you just have the usual train apply methods. So this is how we train a Gaussian process. Don't worry about those guys here, just do them to suppress output here in the notebook. So we apply them, we get some predictions, and now let's plot them. This is what you get from the prediction. So here's a plain regression. So this is all nice, but we could have done this before, right? But I've told you about all these distributions, and we can actually ask the Gaussian process now, please give me the mean prediction, this is the red line here, but also please give me the variance of the Gaussian distribution over the predictions. And then I can plot something like the 95% confidence region, while multiplying with this constant times the square root of the variance. So I get something like this. So the model tells me, I'm really sure about this gray area here, and this is the mean. Well, you might say this is nice, but we can do even nicer. We can actually visualize the density function of the predictions. So at every testing point here, we evaluate the probability at each point and color them. Then what we get is something like this. which is now a full predictive distribution over this regression problem. And in particular, you see, here's a point, if you can't see it, and here's a point, and in between, the density kind of goes down. So the model is kind of aware of that there's nothing happening in there for this particular kernel choice we've made. And also in here. Whereas where there are a lot of points, it kind of says, well, I'm pretty certain about my predictions in here. Okay, now I've told you, well, I've just chosen an arbitrary kernel width, just set it to once. We can optimize actually those with Shogun. I won't go through the code because it's a bit painful to construct all the parameters. We are working to simplify this, but it's easy. It's not magic or anything. So if we do this, we have some model selection class. We tell it, please select the model. We get the best parameter point estimates. We apply them to a machine, which is in this case the Gaussian process, and we train again. We plot again everything, and then we get something like this, which is now the kind of the best model that this thing can come up with. You still have this gap here, for example. Here the density is lower, but it kind of resembles the sine wave quite nice. And all this model selection now work without any trying random parameters that you specified before, but just via gradient descent. Okay, this is one for regression. And now I told you this Roman guy from Siberia, he's doing a great job currently in implementing classification methods. And actually last week he has finished one of them, so I just wanted to show this because it's quite cool. He uses probit regression. So as a likelihood, he uses the CDF, the cumulative distribution function of a Gaussian, which looks like a sigmoid. It has a really similar shape, but the nice thing is that you can also, if you multiply it, if you convolve it with a Gaussian, it stays Gaussian because it's a CDF function of a Gaussian. And then I create some nice data here, some point clouds, and I create my Gaussian process. And now notice this is pretty similar: zero mean function, Gaussian kernel, but now probit likelihood and Laplacian inference method, because we have to do tricks to solve the integrals. Plug it in. We can again train. We can get mean predictions. And we also can get the certainty values for the predictions here by asking the labels for give me your values, and we can plot it. We get something like this. This now looks really similar to the output of an SVM, but all this is proper probability, so it's not just random distances, but it's proper calibrated. So if we do some kind of scoring algorithm like an area under the curve, something like this, this usually is a nice thing to do. So this Laplace approximation, the solution of this is actually pretty similar to the solution of an SVM. So these things are related a lot. But we're working on extending this for multi-class, for doing more fancy inference problems, and then also to consider distribution of our model parameters to get better performance. Okay, nice. Where are my slides, Dylan? Okay. Sorry. Okay, this was it for Gaussian processes. Yeah, this is just basic ideas, hopefully not too many integral signs. Now the last few minutes, maybe you all just do a quick reset in the brain. In the last 50 minutes or so, I'll be talking about those kernel methods for hypothesis testing, but maybe also some questions for the GPs. Any particular things? Yes?
Yes, I have one. So it's great to have this all in Shogun. That's great. Good job. So I was wondering, I mean, with the SVMs, I mean, there was a lot of focus on getting this large scale and so on. So, and I know the Gaussian processes usually are a bit smaller scale, but what is the scale which is kind of reasonable I mean, the number of examples, what is reasonable right now?
So maybe let's talk about regression for this. So I've told you we have to compute this with a joint Gaussian distribution, and we have to condition it. And this involves those expressions here. And you'll see there's an inverse of a kernel matrix. So this is O of n cubed, just in the plain form. So you kind of, you can't do more than, say, 10,000. Then it stops for now for the plain implementation. However, you can use more sophisticated likelihood functions and combine them with more sophisticated ways to do inference. For example, you can have sparse Gaussian process regression. This way, what basically happens is you assign some weights to your training examples, and you put some kind of L1 constraint on them, which then enforces sparsity. And this way, you don't have to invert the full kernel matrix, but only subsets of it. So this is one possibility you can do. Then, as for the kernels and this fast food stuff, you can do things like you can do lower rank approximations of the kernel matrices, for example, with incomplete Cholesky factorization and similar stuff. But it's very true that so this doesn't scale up as well as these support vector machines.
Yeah, maybe the GPs have, I think, much more CPU cycles per gigabyte of data, kind of, right? So maybe here the GPU implementation would be very useful.
I mean, the thing is, if you're having huge amounts of data, then you don't really need sophisticated models to model them, right? So if you have billions of training examples in very high dimensions, you don't need like a massive nonlinear classifier to do stuff with them, right?
You might still need a nonlinear classifier, but maybe it's much easier to estimate, for instance, posterior probabilities, or I mean,
exactly.
So, but I mean, if you have a lot of data, maybe you still want to learn a complex function.
Yeah. So, I mean, that's true. But I mean, in general, those things are more suited to smaller scale problems. So especially this integrating out hyperparameter models. This one here. This one it's massively expensive, and it gives you really, really nice uncertainty results for smaller scale data sets. So those things are not really meant to work on billions of examples. You can obviously do tricks, but I would say so in their most general form, no, not really.
Okay, thanks.